All right, this should be fine. For anyone who does not know, when I grade your exams and your quizzes, you get a score here, and I upload the assignment with comments on like where you got points and where you lost points and stuff. Please look at those. For the exams, I don't do comments. I might start recording comments too. That might be kind of fun. So check out those comments so you can always know exactly what you did right. All right. So that is an option for your quiz tomorrow. You do have a quiz tomorrow, remember? Your quiz tomorrow is going to be on 5.3 and 6.1. Again, you always know exactly what your quiz is going to be on because it's always going to be on the same material as the homework. Okay, so 5.3 and 6.1 are due tomorrow. So tomorrow's quiz will be on 5.3 and 6.1. Okay, then 6.2 will be due on Thursday, which means Thursday's exam will be on quiz will be on 6.2. And next Tuesday will be 6.3, 6.4, maybe 6.5, okay, etc. So we're nearing the home stretch, right? Talking about exponentials today, then graphs, then logarithms, then graphs of those, then properties of logarithms in 6.5, equations in 6.6. That's a good section. And then the last section will be applications. These 4 sections are going to be kind of quick. But the last 3 sections of the class are going to be long. Okay. The end of this class is going to be some deep, thick material. No logarithms today. Your wish is my command. I got it. So we're just going to do exponentials. So we're going to do a little bit of exploration. Okay. A little bit of math exploration. Doesn't really work. We're going to do some exploring. Okay. If we invest $1, I'll tell you the story about my ex-mother-in-law at the end of class today. Okay. Beginning of class, you already got the wig. End of class is when it'll be there. So for people who don't care about my personal life, you don't have to be subjected to that. Okay, so we're investing $1, smaller investment than Bella invest. Bella invested something quadrillion dollars, like $9 quadrillion on Friday. But we're investing $1 at 100% interest. Wow, that's quite the deal for 1 year. How does that value change with n? So remember back, right? We had our compound interest formula that the amount after time t is our principal, our original investment, our $1 here, times 1 plus r, interest rate, divided by n, number of times it compounds every year, times nt. Okay, so the question is, how does n, the compounding, change things? Well, let's look at something together. Okay, we're exploring together. Let's see. Gonna do some exploring. Let's explore with our friend Google. Okay. So if actually, yeah, let's not do that way. Right? Let's say we invest like $2,000, 1 plus interest rate of 2%. Why not? Let's have n equals 1. Then after a year, if it compounds once a year, we'd have $2,000 and $2,040. But if we change n to be 2, if it compounds more, the question is, will we have more money if it compounds more or less money? For example, here it's compounding annually. Will we get more money if it compounds monthly? Or will we have less money if it compounds monthly? What do we as an investor want from our investment for how it compounds? Does compounding more help or hurt us as the investor? That's the question that we're going to address right now. And of course, we can just see it by changing this value. Change the value. We get 20 extra cents if it compounds semi-annually. Whoa, that's huge, 20 extra cents, okay? And that's sort of what we're gonna show right now. And I just got a genius idea. We're gonna talk about it right now for how to show this next thing. So the question we're doing, this exploration, if we invest $1 at 100% interest for 1 year, how does that value change with n? So that's going to be a of 1 is going to be our principal, which is $1, times 1 plus r, which is 100%, divided by n, raised to the n times t after 1 year. Question is, how does this compounding thing change it? So we're going to do some spreadsheeting, okay? All right, our formula here, invest $1 at 100% interest rate for 1 year. The formula then is just a of 1 is going to be 1 times 1 plus 1 over n raised to the n times 1. Okay, so let's look at that. Let's make a table. And let's see how it changes. Okay. That's some big font for big fun. Okay, so if n is 1, right, then we just get 1 times 1 plus 1 over that raised to the that times 1. You make it bigger. Make it all bigger. Everything, size 36 font. We're gonna have a nice table. Okay. If it compounds annually, then after 1 year, we will have $2. The question is, how does this change as things go on? Boo! Let's not do that like that. If it compounds semi-annually, right? How much are we going to have? $2.25. What if it compounds quarterly? Remember, quarterly is when n is 2. We're going to, we're going to have about $2.44. So it keeps on growing, right? The more it compounds, the more money that we're going to have. It compounds monthly. That's n equals 12. $2.61. So yeah, look at how much extra money we're making now. What if it compounds daily? Or even hourly? Or what if it compounds every second? The daily would be 365. $2.71. Hourly will be 8,760. That's still $2.72 now. So notice, right? As it compounds more frequently, it's growing. But the amount it grows by is slowing. It's slowing. What about every second? That means n is 31 million seconds. Oh, gosh darn it, I missed an opportunity. I really missed an opportunity. We're going back. How many minutes, right? How many minutes are there in a year? 525,600 minutes. Anybody? Again, $2.72. We did seconds. This is the last one, I promise. We did seconds. Yeah, it's from the musical Rent. Still $2.72, but it's getting bigger. So the question is, what is this number? It's approaching a number. The question is, what is it? The answer is E. Euler's number. 2.71828 ... is Euler's number. Okay? And that's what we're talking about today. We're going to be talking about an Euler's number, which is very, very, very common in dealing with exponential equations. Okay? So, see spreadsheet. So, as n approaches infinity, as n gets really big, as we compound more and more, it approaches Euler's number, E, which is about 2.718282 ... Okay, and this number appears everywhere. Okay, very common if you know anything about probability, the standard normal distribution, the bell curve, Gaussian distribution, that Euler's number is huge there. It's really popular in calculus as well, because derivatives and integrals can be sometimes tough, but if you take the derivative of e to the x, it's just itself. Again, this is an exponential function. Whereas if you take the derivative of something like 2 to the x, this is also an exponential function. This is much messier. It's 2 to the x times the natural log of 2. And you may not believe this, but some people don't like natural logs. Okay? So having this base of the exponential be e is really nice for applications of calculus as well. Euler's number is also huge in probability. Okay, it pops up. I already said it a little bit with distributions and stuff, but there's some really cool facts about, like, if you try something 2 times and you have a 1/2 chance of it, what do things become 5 times and you have a 1/5 chance? What are the chances that you get at least 1? And those probability distributions have a lot to do with this number. Okay, so there's all this cool stuff. Oh, don't worry about this. This is calculus. Don't worry about calculus just yet. But there's a lot of stuff going on. Really, what I'm trying to do is just say, hey, there's some cool stuff going on. If you compound more and more, you approach this special number, Euler's number. Okay? So what you need to know is continuous compound interest. Because most of that I'm just ranting about some cool math stuff. But for this class, this is what we're going to talk about next. So there's a formula. A of t equals PE to the RT. Okay? So this is to be juxtaposed with compounded interest like this, right? We have 2 equations. One for continuously compounded interest and one for normal compounded interest. Notice that these formulas are similar. They have a P in front. They have an RT up front. But if something is continuously compounding instead of every month or year or 2 months, then the base of the exponential function is Euler's number E, 2.71828 ... Okay, so what do we mean by continuously compounding interest? This is way too itchy. No more. Oh! I lost my glasses. So what do we mean by continuously compounding interest? Normal interest, right? Normal interest is going to be like, it only compounds at certain times. Right? Normal interest. Say it compounds every year. Well, then your $1,000 sits in the account until a year, and then you get your interest. and it sits in the account for another year. You get your interest again and again and again and again, right? The interest only happens sometimes. Continuously compounding interest means it's always growing. This is continuous. That's what's kind of going on here. We have an exponential function. So if we have continuously compounding interest, this is our formula. P is the principal, just like before. R is the interest rate, just as before. And E is Euler's number, that 2.71828, etc. Okay? So it's crazy that such a weird number, an irrational number, can pop up here. Well, let's actually use it. Okay? Let's actually use this. Example 3. So, example 3 was supposed to be like example 2. It was supposed to be like the example we did on Friday where we had Bella invest some money. And I was going to say, well, now in example 3, let's compare that with what would happen if it was continuously compounded. But we're not going to do Bella's example again. We're going to do a new example. Okay? Let's say Joe Smart invests, let's say, $1,000 at an interest rate of 2.5% for 5 years. And we're going to ask some questions about Joe's money. Okay? So part A. How much will he have if it compounds annually? Okay? So we're going to look at 3 things here. How much is he going to have after 5 years if it compounds annually? How much will he have after 5 years if it compounds monthly? And then what happens if it compounds continuously? Okay? So again, annually means that $1,000 is just going to sit in the bank, no changes, or wherever he's investing it, just sitting there. And then after a year, boom, get your interest. Here you go. Thank you very much. Monthly means it just sits there, but after a month, you get a little bit of the interest. Then after another month, you get a little bit more interest. Then after another month, a little bit more interest. Continuous means every second that goes by, you're getting a tiny little trickle of interest. All right? So let's see how this all compares. If it compounds annually, again, we need our formula. A of t equals the principal times 1 plus r over n to the nt. And we just have to identify what everything is. So we're curious after 5 years, so t is 5. We're investing 1,000, so p is 1,000. Our interest rate is 2.5%. Okay, it's getting a little breezy. So we need to answer. How do we write 2.5% as a decimal? Okay, I'm going to go close my window, and you're going to tell me how is 2.5% as a decimal? What is r going to be here? Yeah, 0.025. Good, good. It's going to be 0.025. N, it's annually, so 1 time a year, to the n times t, which is 5. All right, and again, we just plug this into our calculator. Okay, 1,000 times 1 plus 0.025 divided by 1, raised to the 1 times 5. And you're going to get about $1,131.41. A lot of ones. Okay, so invest this 2.5%. You have an extra $131 after a year. The question is, how about monthly? Okay, it's the same thing, but now n is 12. N is how many times a year it compounds. So if it's annually, right, that's n is 1. Monthly, n is 12. So you just do something very similar. If 5 is going to be 1,000, just change the n to 12. 1 plus 0.025 divided by 12 now to the 12 times 5. And notice how this formula changes, right? Here's our compounding part. Remember, our formula for exponential functions, remember all the way back to Friday, was a times b to the x, where a is the initial amount and b is the growth rate. B is this whole thing in parentheses. So notice how the growth rate changes. It's getting divided by 12 now. The growth rate is much smaller. It's like we have 1/12 of the interest rate. But our exponent becomes much bigger because we're now getting that interest 12 times in a year. So we're getting the interest 60 times instead of only 5 times, because it happens 12 times a year. We're having 60 of these interests instead of only 5. But again, the interest is smaller. We're just doing it more every month, but smaller every month. Okay? So again, just type that into your calculator as well. And what you get is about $1,133.00. So again, if it compounds monthly instead of annually, you get about $1.50 extra. So the more it compounds, the more you're going to make. But really, it doesn't change it by that much. Okay? But it is something that you can think about, especially like for like car payments and stuff, right? The more that something compounds, there's actually a ton of stuff to be talking about, like for finance. The more something compounds, the bigger the number is going to be, the more often, but actually not that much. And again, also, the more you can pay off of your principal, the less interest you're going to have to pay over time, just stuff like that. But that's actually a different class, not ours. We'll include it where we can. Okay. And the last thing is, how about if it compounds continuously? So we can't use this formula anymore. This formula is only if we have an n. If it compounds at once a year, twice a year, 4 times a year, 12 times a year, 20 times a year, 5 million times a year. But if it compounds continuously, we need to use our continuously compound interest formula. We need to use that other formula, A of t is equal to p e to the rt. Again, a times b to the x is exponential growth. Initial, our growth rate is e now instead of this mess in the parentheses. Okay, and our interest rate becomes our exponent. So after 5 years, if it compounds continuously, our principal is still $1,000. P is still 1,000. E is Euler's number, not a variable. This is a number. It doesn't look like a number. All right, R is still 0.025, just like before. And T is still 5 years. So hopefully you can locate your E number on your calculator. Your calculator should have them. If your calculator does not have an E button, what it should have is like an E caret button, or it might be labeled E to the X. And if you use the E to the X button, this should pop up on your calculator. So on your calculator, what will look like when you type this in is something like 1,000 times E caret 0.025 times 5. It's very important before your quiz on this. This material will be on Thursday's quiz. It's very important before your quiz that you are comfortable being able to type in Euler's number and functions involving Euler's number on your calculator. Okay, if you have any questions about that, you can just take a picture of your calculator, send it to me, and I can show you where it is or help you with it. Okay, but you should know how to be able to, you should be able to type this in. So we do that, we get 1,000 times e raised to the 0.025 times 5. And we get approximately at $1,133.15. So if it compounds continuously as opposed to monthly, you get an extra 15 cents. Good work, Joe. So Joe Smart would like it to compound continuously. Get those 15 cents. 15 cents saved is 15 cents earned. That's not the phrase. Okay. So last thing we're going to talk about is the difference between growth and decay. Then we're going to be done with this section. We're going to be done early today. Today's a nice early day. Let's see, attendance question before we do the last problem. Attendance question today will be, I had a really good idea. I forgot it. Do you like soft cookies, like chewy cookies, or harder cookies? What side of the middle do you prefer for cookies? That's the attendance question for today. Softer or harder? Chewier or crunchier, I guess. Okay? And there is a right answer, by the way. If you get the wrong answer, you get -5 points on your next exam. Okay? That's a lie, but maybe it'll give you some motivation to get the right answer. Like, it's not even a close question in my mind. I feel very passionate about this. Okay, so let's do the last problem. So again, let's go back to the beginning of this section. We said exponential growth was something like y equals ab to the x. Well, sometimes b is Euler's number. Okay, so there's a lot of different ways of thinking about this, right? We said this is exponential growth over here. If b is bigger than 1. And we said it was decay if b is less than 1. This is what we talked about at the beginning of the section. Okay, now we're going to talk about what does it look like if we have e as our growth rate. All right, I don't have room here. Gonna need a new piece of paper. All right, now that most people have answered, if not everybody, I am glad that Lexi, Gabe, and Delaney understand. Because I have met a lot of people. Well, actually, I'm not going to trash talk you if you disagree with me. If you disagree with me, that's fine. So this is what things look like if you have a growth rate of like b. Again, some examples of this are like y equals 5 times 3 to the x. That means we initially have 5 people, and then they triple every unit of time. Or decay would be something like 5 times 1/2 to the x. We initially have 5 people, but then every day we lose half of them or something. Let's not talk about people. Could be radioactive decay. Half-lives. We're going to start talking about half-lives and like radioactive decay later on in this chapter. Okay, but let's say we don't have b. Let's say that we have e. Okay. Also, we can look at growth and decay like this. A e to the RT is exponential growth. A e to the negative RT is exponential decay. So there's a lot of different ways of talking about exponential growth and decay. If you're ever curious, you can just plug in some numbers and see what happens. So last example of the day, before we call it an early day and say, you know what? We don't need to talk about math. We're going to end a little bit early and just do some extra problems from the homework. Okay, that's what you can do with this extra time when we finish this example. You can have a nice, relaxing day. It's a little breezy outside in Rock Springs, but you can go outside, sit up at a picnic table, do some extra problems from the homework assignment, or you don't have to. Are the following exponential growth, or decay. Part A. Y equals 2 times 5 to the x. Part B. Y equals e to the x. Part C. Y equals 3 to the negative x. Part D. Y equals 1/2 to the x. And part E. Y equals 3 times e to the negative 2x. Okay, so what we're going to do is we're going to go through these and talk about, are they growth, are they decay, and what they represent. Okay, what are the starting values? What's the growth rate? What is this function going to look like? Okay, so this first one, 2 times 5 to the x. Growth or decay? Somebody tell me. Growth, good, good. And the growth rate is 5. This first one is growth. Oh, quadruple good. Quadruple good for you guys. All right. We initially have 2, and then every unit of time, or whatever it is, it quintuples. Okay. So this is growth. What about B and C? Yes. Great work, Gabe. Not even just good. Great, fantastic, amazing. Now give me B and C. Yep, B is growth, C is decay. Good, good. And again, the initial value on both of these is the same. The initial value is 1. This is 1 times e to the x. 1 times 3 to the negative x. This one has a 2 in front. These, you can't see anything out in front, so it's a 1. So both of these start with 1. And then the growth rate here is Euler's number, 2.71828, ... Here, the decay rate is actually 1/3. If you wanted to, you could write this as 1/3 to the x. Remember negative exponents? Negative exponent means reciprocal of the base. So these are actually the same thing. Every unit of time we get cut into third. All right, and then likewise, D is also decay. We keep getting halved. Initial value is also 1. And part E is also decay. Here we start with 3. The decay rate is E. And then we have an exponent of -2. And because we have a negative exponent, it's decay. All right. And I'm not probably going to ask you any trick questions, but the book might have something tricky. I don't remember whether it does, right? It could have something tricky like this. This, you might think we have a fraction, so it's decay. It's like a fraction and a negative exponent. Is this far enough up, Gabe? It's a fraction and a negative exponent, so they sort of cancel each other out. This is growth as well, but it kind of looks weird. You could also write this as 2 times 2 to the positive x. All right, so just analyzing what things are growth, what things are decay. All right, so that's the whole section. All right, so we are done for the day. Finishing, what is that? 40 minutes early. We'll start the next section and should have time for some review tomorrow. Your quiz tomorrow will only be on 5.3 and 6.1. 5.3 was like graphing polynomials. 6.1 is this stuff. Okay. There's going to be a lot of interest questions in this section. Okay. Compounded interest and continually compounded interest. So watch out for those two formulas as well. So we're done with class. If you want to hear the story, it's story time. You don't want to hear the story? Goodbye. Have a great day. So this is the story. So my ex and I, we keep in touch. The relationship didn't work out, but we don't hate each other. And so she's dating this guy, and the guy has some kids. And she's been dating this guy for maybe like, I don't know, like 2 months or something. And so what Nancy does is she made this box of like a whole bunch of garbage toys, just like super random toys that you don't, anyway, just a bunch of random garbage, okay, and she mails them to Danny's boyfriend for the kids. And they've been dating 2 months. That's super weird, right? Like, can you imagine you have kids and then you start dating someone and then all of a sudden their stepmom just sends you random gifts for your kids? Like, what? Like, I feel bad for the guy. Like, it's not often that you feel bad for your ex's boyfriend, but oh my word. She told me that story and I love it. I love hearing Nancy's stories. I hope she doesn't know about this channel. Anyway, that was my story. But I thought it was funny. I try to get Nancy updates every once in a while. I don't know. I think I may have said this before, but on the day that I helped my wife, or my ex, I guess now, pack her stuff, I said to her, and this is maybe this is terrible, but I said to her, the best thing about this divorce is I never have to talk to Nancy again. I literally said that to her. And I think that's maybe mean. I don't know. But that's all the Nancy stories that you get today. We'll be back again tomorrow talking about 6.2. Hope you guys have a good day. Bye-bye. I think she kind of laughed, but I think I don't know. I think she was maybe a little emotional on that day. Understandably so, right? But I thought it was kind of funny, but maybe a little mean. Bye-bye.